So now we are on part 5 of our 6-part exam for Transport 1. In our last video, we found our stability requirement for our results or for our code to implement that stability when calculating our initial temperatures for our temperature profile, time varying temperature profile. And now what we're going to do is we're going to derive our Crank-Nicolson's finite differencing scheme for our heat diffusion equation, in which we'll show that there are no stability constraints. And this is the last thing we need to do also to finish our code and to solve our problem and plot those results. So first thing we're going to do, I have our finite differencing scheme and our heat diffusion equation. And we're going to take the second derivative of that equation. And that is going to be Tj n, and R is, we know that R is alpha, our thermal diffusivity times our change in time over our change in position squared. And so for this derivation, we're gonna, instead of writing R, we're going to write out our expression for R. So Jn times alpha times delta T over delta X squared. Yep, that's a 2. And then we're going to do Tj in our position time plus 1 minus R2 initial time and positions minus Tj and minus 1, and then we are going to add add by that. It's a lot of writing. This is going to be J plus 1, our position plus 1, and this is going to be our position minus 1. And then we divide Right, and then we're going to divide all of that by 2 to get the average of our calculations for those temperatures. Okay. Excuse me. All right, so what we need to do next is we need to bring our R expression here, which is that right there, out of our this right side of our equation. So we're gonna write this like negative R T J n plus 1 position plus 1 minus 2R Tjn plus 1 minus R Tjn plus 1 minus 1, and equal that to the right side, which is just going to be R times T time 1 position plus 1 minus 1 plus 2R times the initial position and time of our temperature, and n plus r times t in minus 1, or position minus 1. Put a parentheses there. Okay. And so now we are going to put in our expression that we solved and proved in part 1, and we're going to add that into our expression here. And that's going to be tjn plus 1 minus r times e to the I k times delta x plus 1 plus 2r minus r times e to the I k delta x. And then we're going to, for the right side, we're going to do the same thing. N is going to be r times e to the I k delta x plus 1 minus 2r plus r times e to the I k delta x. Alright, now what we're going to do is we're going to simplify this expression. We're going to go ahead and get our increment in time of our position, or increments of our temperature with position and time by itself. And that is gonna be 1 minus 2r times 1 minus cos our von Neumann stability analysis times k delta x over or plus 1 minus 2r over 1 plus 2r minus cos k delta x. And then that's going to be multiplied by tjn. Excuse me. Alright, and so the next step is for this expression, we're going to relate our functions that we have here to y. And we're going to do that by writing tj tjn times 1 minus 2ry over 1 plus 2ry greater than 0. Alright. So now that we have that, we can now that we have this expression, we can use it for our matrix that we're going to build using our simultaneous expressions to solve for our problem, and we're going to use that matrix to stabilize our results in our code in the next video. So we can also write this as 1 minus a over, well, this is how we're going to write it in our code. So basically, we're going to use a for stability in our code, but we don't need to add that here yet. So basically, a needs to be less than 1, but greater than 0. In order for us to have no stability constraints. And then I'm gonna erase this, and we're gonna take all of our expressions that we did, and we're gonna put that into a matrix for our list of linear equations. Alrighty, so now that I've erased the board, we're just going to set up our matrix from our expressions we just derived. And this matrix is going to help us solve for our linear set of equations in our code in our next video. So for the left-hand side, we have our expression. So for our uniform bar, let's start with that. We have 1, 2, 3, 4, 5 initial temperature values, or temperatures to calculate. This is going to be T0 and we're going to index this as the end of the bar in our code, and T0 is going to be the beginning of our bar. And so we're going to calculate for the initial temperatures in each increment of that bar using our matrix. So we're going to have T1 n plus 1 to calculate that temperature, T2 n plus 1, T3 n plus 1, T4 n plus 1, and T5 n plus 1. Okay, and then for those values in our expression, we have a 1 plus 2r, a 1 plus 2r, a 1 plus 2r, and a 1 plus 2r to calculate for those. And then for each on the left hand and right hand side of our expression, we have our negative value of our R expression, and so we'll just do, we only need 3 of them to calculate the inner temperatures. Okay, and so we're going to set that up in our code as A for our matrix. A is going to be our left-hand side of our expression. And then for the right-hand side, we have B, which we'll label it in our code. And for B, we're going to calculate the initial temperatures in a vector. So we're going to have R T2 n plus 1 minus 2r times the temperature at 1 plus tr, or not tr, plus r times t at the beginning, plus to times r. All right, and then we're just going to do the same for 3, 4, and 5. I'm going to calculate that by, just get this in there real quick, times T2 n plus R T1 n, and for the initial, that's 3 and this is 4. 3, 4 plus 1 minus 2r T3n plus r T2n, and then for RT5 time 1 minus 2r times T4n plus RT3. All right. And so we're going to use this vector and this matrix that we set up. I'm going to use that as our expression in the final of our code, and that is going to solve our time varying temperature profile and the temperatures at each increment. We'll graph that, and we'll use our Crank-Nicolson finite differencing scheme to allow for more stability in those results.